friends and physics loving people. I'm back here with another video on the applications of time independent Schrödinger equation, example number 5. This being a very important problem in quantum mechanics, the linear harmonic oscillator. It formulates the theory of radiation, quantization of lattice vibrations, etc., and as well as different basic illustration regarding quantum mechanical systems. We now define the potential energy of the linear harmonic oscillator, which we always know as given by equation 1, where m is the mass, omega is the angular frequency, and x is the displacement. So putting this potential in the TISC, we have this kind of equation 2, where this bx part is replaced by half omega square x square. And to solve equation 2, we define a dimensionless variable xi equal to alpha x by as in equation 3, where alpha is in terms of the known parameters m, omega, and h cos as given by equation 4. We do some modifications like this and also put another variable lambda here, where lambda is equal to twice m by s square alpha as given by equation 4. When put it here, we get lambda equal to twice e by s cos omega, leading to e equal to half of lambda s cos omega as given by equation 5. This equation will be used later on. Now our equation 2 is now in a simple form as given by equation 6 after all these modifications that we made with the help of equation 3 and 4. Solving equation 6 is done in a very clever way. We first put lambda equal to 1 and check it for the range x tends to plus minus infinity. If x tends to plus minus infinity, it represents also xi also going from minus infinity to plus infinity. So with lambda equal to 1 and in the region x tends to plus minus infinity, we have this kind of solutions for equation 6. Equation 6 produces a solutions e to the power plus xi squared by 2 and e to the e minus xi squared by 2. Now if we put xi equal to plus minus infinity as it is in a asymptotic region, we'll find that this part will lead to some infinity, and that's why it is not a well-behaved wave function and is discarded right on. So we are left with now this e to the power minus xi squared by 2 term, and will be incorporated this term while solving the Schrödinger equation. We must remember that we are taking only lambda equal to 1 and as well as considering xi tends to plus minus infinity, or rather we are finding a symptotic solution to equation 6. But thing is that we can incorporate this factor, but the general solution is not this factor only. We have to put another factor just like phi as a function of xi, which we need to determine in order to know the total function u, or total function this ux or u xi as given by equation 7. So this term will be there because already for lambda equal to 1 this term is present here, and that's why this term will be definitely be a solution of the wave function. But to cover up all the things, we have to put another factor pi as a function of xi in order to find a total wave function whether as a function of x or xi as given by 7. Now to solve 7th, to solve 6 we put 7 in it, and equation 6 now become this one. So the equation 6 is no longer in terms of u now, it's in terms of phi now, and helping us to find out phi now. Once we find phi, we can find u, and that will be the wave function that we want. Now equation 8 is the equation, time independent Schrödinger equation, that is incorporating with phi, and we need to solve this equation 8. And for that we use the famous Frobenius method in find series solution, and with a solution like this, coefficients a sigma, xi to the power sigma plus a xi sigma plus 1, xi to the power sigma plus 1, which put in a summation like this, as xi to the power s, where s goes from sigma to infinity, equation 9. So putting this 9 back in equation 8, we get an equation like this. It's clear from equation 9 that if you differentiate one time, it will give us as into s into xi to the power s minus 1. Double differentiation would give us as s into s minus 1, xi to the power s minus 2, which is shown here in equation 10. So this is nothing but just simply there's double differentiation and single differentiation as being done here, as being implemented here in equation 8. Now it's clear that right hand side is 0, this right hand side of 10 is 0, so definitely all this term would lead to 0, and the thing is that a coefficient of each power of xi must be vanished separately, because they have different coefficients, so they must separately vanish out. So one thing that this xi has a coefficient of this xi has a power of s, this xi has a power of s, but this xi has a power of s minus 2. So while equating the coefficients, we have to put this s equal to s minus 2 equal to s. In that sense, our s would become s plus 2, this s would become s plus 2, and then s minus 1 would become s plus 1. So this particular term would now become s plus 2 into s plus 2 into s plus 1 xi to the power s. Now we can compare all these coefficients, and comparing all these coefficients we get a relation like this: s plus 2 within bracket s plus 2 into s plus 1 minus s twice s minus lambda minus 1 equal to 0. So all these terms, all the coefficients of xi to the power s is now taken to be 0, and this is the condition that we have. So simplifying all these things, we get equation 11, where these particular terms are representing the ratio of the coefficients in the series solution as given by equation 9. This being a very famous recurrent equation as we encountered in our mathematical physics course, and this equation particularly helps us to find out the different coefficients once we find one coefficient, suppose as. Now in this equation, if you put s tends to infinity, we will see that this as plus 2 by s going to 2 by s. This is very clear here, because all this term would go only for s tends to infinity, and they would cancel out, and this 2 will be there, and on the denominator it will be s square will be there, so s is cancelled, so it will be 2 by s here. So equation 12 in the limit equation 11 in the limit s tends to infinity becomes 2 by s. Okay, now our main aim is now to find out what is the form of this pi as a function of xi, and then it will be helped by this equation 11 in finding the form of phi as a function of xi. We'll see that this pi is an infinite, since it's an infinite series. We put it like this form. We've said that this is equal to this, and since we know that e to the power x is equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and so we put this equal to this. So putting all these things in a summation convention, we put that this e to the power xi square is equal to summation bs xi to the power s, where s goes from 0 to 4. Now this coefficient bs can be found out like this, and they are nothing that the coefficients of b xi to the power s plus 2. If we put xi s plus 2 and here xi s, we get like this kind of relations. So bs plus 2 divided by bs is now this, which is equal to 1 by s by 2 plus 1. So this is the relation for relation for the ratio between the coefficients in the series expansion of this e to the power xi square. Now if you put s tends to infinity, we'll say that this term 2 by s, this 2 by s will be now will be very large as compared to 1, and 1 will be neglected, and this becomes 2 by s. Now your bs plus 2 by bs is now similar as as plus 2 by s, as we have already pointed out. So in the sense that our coefficient bs is no longer different from as, and in the sense that this pi is now e to the power xi square. So our form of phi is now e to the power xi square, and putting this expression e to the power xi square back in equation 7 here, our u as a function of x or e to the function of xi will now become e to the power plus xi square by 2, because this is e to the power xi square. This e to the power xi square cancel with this minus xi square by 2, and it will be e to the power xi square by plus xi square by 2. So our solution is now e to the power xi square by 2. But if we put these conditions that xi tends to plus minus infinity, you will see that this term will always give us some kind of diverging results, because it's an infinite quantity for this condition xi plus minus infinity. So in the sense that we cannot use now a infinite series for phi now. This is clear. Now how to come out of this problem? The answer is that we put some certain special value for lambda and cut the infinite series to a limited one. That means our infinite series is no longer an infinite series. It would become a polynomial. So we put lambda minus 1 equal to some even integer say twice n, that is lambda equal to now twice n plus 1, and also all the terms beyond n are now 0. That the coefficients ending at n is no longer 0, but above that, beyond that, all the terms are 0. That is n plus 1 is 0, n plus 3 is 0, like that. So we cut off the series and with a particular value of lambda equal to twice n plus 1. And we can also show by equation 11 that this kind of coefficients will vanish while these coefficients will remain depending on the odd or even values of n. Coming back to the thing that lambda equal to twice n plus 1, as already we know that lambda equal to twice e by s cos omega, we see that e is now n plus half s cos omega. N is put as a subscript because e now depends on n, that's why we put a subscript, and with n values going from 0, 1, 2, 3, 4, 5 like this. So equation 12 gives us the energy levels of the linear harmonic oscillator, and this particular expression now can be shown to have equal distance between the different energy levels as given in equation 13. If you put n equal to 0 here, it will be E0 will be equal to half of s cos omega. If you put n equal to 1, it will be 3 by 2 s cos omega. If you subtract E1 from E0, E1 minus E0, then it will be s cos omega, which is shown as a generalized condition 13. En minus 1 is s cos omega. So the energy levels will be equidistant with a difference of s cos omega. So equation 12 give us the energy levels or the energy eigenvalues for a linear harmonic oscillator, which is coming from the condition lambda equal to twice n plus 1, while restricting out the infinite series to a polynomial, just done here. And as we see that this pi, when behaves like an infinite series, cannot lead to a well-behaved wave function. It leads to a expression like e to the power plus xi squared by 2. Well, now let's also define one term, that is, if you put n equal to 0, this energy is known as 0-point energy as given by equation 14. This is a very important concept. It is possible only in quantum mechanics that a particle have energy in the ground state and known as 0-point energy. Now coming back to the solution of the equation, we put lambda equal to twice n plus 1 in equation 8. Now 8 is becoming equation 15. This equation is a very familiar equation in differential equation concept or a mathematical physics. So this equation leads to solutions which are known as Hermite polynomials. Sum of the Hermite polynomials with n equal to 0, it is equal to 1. With n equal to 1, it is twice xi, and like this. So we are now at a position with lambda equal to twice n plus 1. We can solve the equation for phi and find the form of phi. Now phi is now nothing, it is simply Hermite polynomials. Phi xi is nothing but it's a Hermite polynomial Hn. And with this, our wave function is now, as from equation 7, is this one. Your ux or u xi is equal to e to the power minus xi squared by 2 into Hermite polynomials, into Hermite polynomial Hn. Since we have to normalize the wave function, so we normalize it, and after normalization, this is the total wave function for the linear harmonic oscillator. This part is from the condition that lambda equal to 1, considering the cases xi going from plus minus infinity, and this part is from the condition that lambda is taking a particular value twice n plus 1 and restricting up the infinite series to a polynomial. So it and with integration of these things, or using the normalization condition, normalization constant can be found out to be this one as given by equation 17. So with all this, we find that linear harmonic oscillator problem can be solved only if we consider a particular value lambda, that is lambda equal to twice n plus 1, and restrict the infinite series for that function phi to infinite polynomial, just keeping the terms only up to coefficient n, and beyond that all the coefficients coming out to be 0. And with all this we finally have a differential equation of the form 15, and which is a well-known equation leading to our Hermite polynomials. Incorporating this part of phi as Hn Hermite polynomials, our total wave function is this, and when normalized we keep a normalization constant n here as given by equation 17. So these are the energy levels. As said earlier, this has a constant difference h cross omega in every energy, between every energy levels, and also we can find the probabilities for LHO. LHO problem is also have a classical description also. The probability for classical description is shown by this dashed lines, where the quantum mechanical is by the solid lines. If you see here, is n is taken to be 0 here, and for if n is taken to be 8, in that case our probability is like this, variation is this, and when average out, we average out the quantum mechanical probabilities, we find that the averaging of the quantum mechanical probabilities is similar to this classical distribution, which is shown by the dashed lines. In this figure, all the solid lines are related to quantum mechanical description, while this dashed lines are for classical distribution. And we see that for large number of energy states, or n tends to infinity, the probability distribution is almost same for classical and quantum mechanical concepts. So with this, we remind the in the first video where we said that for n tends to infinity, our quantum mechanics become classical mechanics, and this is a vivid example of the same. And lastly, we have the assessment, that write the time independent Schrödinger equation for SHO, that is the equation 6, and then the recurrence relation, equation number 11, as plus 2 divided by s. And what do we mean by polynomial? It's a finite series with restrict terms and all the coefficients beyond the terms are 0. And why that this TIC for this LHO leads to a polynomial? Because we don't get well-behaved wave function. We see that our wave function becomes e to the power xi square by 2, and only for a restriction, or that lambda equal to twice n plus 1, and as well as cutting out the infinite series to a polynomial gives us solutions. What is Hermite polynomial? It's simply the solution of equation 15. Is a well-known thing in differential equation, and write few of them already given here, and also the graphical distribution for probabilities in case of classical as well as quantum mechanical. We see that for large quantum mechanical quantum number, the classical pattern assumes the same that of quantum distributions. With all this, I am ending up this video. Hope that this video will be useful for you. Thank you very much. Keep watching, and also never forget to comment on our videos. Thank you very much once more.